Hello, today we are going to cover 8.5, angles of elevation and depression. Students will solve problems involving angles of elevation and depression, and students will use angles of elevation and depression to find the distance between objects. So we have angle of elevation and angle of depression as our new vocab terms. We'll get right to it. So an angle of elevation is the angle formed by a horizontal line and an observer's line of sight to an object above the horizontal line. So we have the horizontal line here. And then we have the person's line of sight to this object. So this is the angle of elevation. Notice the line of sight is above the horizontal line. An angle of depression is the angle formed by a horizontal line and an observer's line of sight to an object below the horizontal line. So notice now we have our horizontal line here. The line of sight is below it, so it goes down. This is our angle of depression. So elevation, go up. Depression, go down from the horizontal lines. All right, and then the horizontal lines are parallel, so the angle of elevation and the angle of depression in the diagram are congruent by the alternate interior angles theorem. So this might be helpful sometime to know that the angle of elevation and the angle of depression are congruent. Now we are going to use our trig information from our previous lesson to solve missing either angles or side lengths. So, at the circus, a person in the audience at ground level watches the high wire routine. A 5'6" tall acrobat is standing on a platform that is 25 feet off the ground. How far is the audience member from the base of the platform? So basically, this is what we're finding here. They already marked an X for us. If the angle of elevation from the audience member's line of sight to the top of the acrobat is 27 degrees. So we actually have everything we need. Notice we always have right triangles here. To be able to do this, we need to have our right triangles. We have those drawn out. So if we have to draw our own diagram, I would suggest always starting with a triangle drawn and go from there. Okay? So first thing I'm going to do is I'm actually going to add this whole thing. So we have 30.5 to the top of her head because this angle they gave us is actually the whole big triangle, not the small one. Okay? So we need to match the information up. We are going to figure out from the person's point of view what trigonometric function we should use. We also have that angle specifically. So we have adjacent is what we are trying to find, and opposite is what we are given for the side length. So we are going to use tangent. So katoa. So we have tangent of our degrees, 27, is equal to opposite, 30.5 over x, adjacent, okay? Now let's see, what are we trying to solve for? How far is the audience member from the base of the platform? Okay, so it doesn't tell us in inches or feet or anything. So because everything is currently in feet, we'll just leave it in feet. We do need to, you can think of this as a cross multiplication if you'd like. Solve for x. Easier if our x is in our numerator, but with it in the denominator, it's not a super big deal. We can still solve for x like this. Now I do want to continue to point out that this works because tangent, cosine, and sine are all just functions that stand in for similar triangles. They're things that mathematicians have figured out. over the years that we can now use, okay? So x is going to equal 59.9 feet. So this viewer is 59.9 feet away. Something on the calculator I also want to point out, you want to make sure that we have degrees showing. We don't want radians. That's something different. We want to make sure we're always dealing in degrees right now. If you get into upper level math classes, we will switch over to radians, but for now, degrees. All right, let's try another one. This one we do have to draw a picture. Like I said, we always use triangles. So it's going to be some sort of triangle, and then we'll fill in our info. At a diving competition, a 6-foot-tall diver stands atop the 32-foot platform. The front edge of the platform projects 5 feet beyond the ends of the pool. The pool itself is 50 feet in length. A camera is set up at the opposite end of the pool, even with the pool's edge. If the camera is angled so that its line of sight extends to the top of the diver's head, what is the camera's angle of elevation to the nearest degree? Okay. This one's kind of crazy. So, it is going to end up just being a triangle, but there's a lot we're doing. So we have a camera here at the edge of the pool. The pool is 50 feet. But the diving board comes in 5 feet. And then the diver, let's look again, a diver stands atop the 32-foot platform. So this is actually way up higher than I had it. So this is up 32 feet. And we're going to say that the diver is up here and he is 6 foot tall. Okay, so crazy picture, right? A camera is set up at the opposite end of the pool, even with the pool's edge, if the camera is angled so that its line of sight extends to the top of the diver's head. So we're looking to the top of the diver's head, right here. What is the camera's angle of elevation? So our question here is, what is this angle? Now we haven't talked about it yet, but an angle is usually denoted by a Greek symbol called theta. It looks something like this, or sometimes I just draw a line through it. That is a theta symbol. That usually means we're solving for an angle versus x or y, although you could just use x or y too. So, what do we know? We know that this is a total of 38 feet. And we know that the camera is actually only 45 feet in that direction. So now we have our triangle drawn. After all of that picturing, we are using this triangle. So we have our SOHCAHTOA. We got to figure out which one to use. We have from the camera, that is our perspective, we have opposite and adjacent. So we need to figure out our degrees. Now, if you recall from the previous lesson, if you were trying to find a degree, you use the inverse. So we have opposite adjacent, we're going to use the inverse of tangent, and then opposite over adjacent. Once you solve this, that will give you your degrees right away. So we have the inverse of tangent of 38 over 45, I believe. Yep. So this comes out to being theta, or the camera's angle of elevation, is 40.2 degrees. So once you get it set up, it's actually not too bad to solve. It just takes a little while to draw the picture. So here the picture is drawn for us. Maria is at the top of a cliff and sees a seal in the water. If the cliff is 40 feet above the water and the angle of depression is 52 degrees, what is the horizontal distance from the seal to the cliff to the nearest foot? So we're trying to find this x. You'll notice they drew the picture. And we have given to us the angle of depression. Now, if you recall, we learned that if we extend this other horizontal line, based on the alternate interior angles theorem, this is actually also 52 degrees. So you could use that, or you could use the fact that this is a 90 and take 90 minus 52. Get 38, and you could use this 38 degrees. It doesn't really matter, but we do need to use the degrees inside the triangle. Okay, so I'm going to use the 38 degrees to solve for x. So this is my perspective from the 38 degrees, because that's the degree I know. I also have the adjacent given to me, and I am trying to find the opposite. So we're doing a lot of tangent stuff here. Once again, we have TOA, SOHCAHTOA. So we have tangent of our degrees, 38, is equal to opposite over adjacent. This one's more simple to solve because we can go ahead and just multiply by 40 on each side. They do want to the nearest foot, so we don't need to change any of our units. We take 40 tangent of 38 degrees, and you get that the seal is 31 round to the nearest foot, 31 feet. It's really like 31¼ feet, but 31 feet. We could even write it out. The seal is 31 feet from the cliff. All right. All right. Another one that I had to draw a picture. Louisa is in a hot air balloon 30 feet above the ground. She sees the landing spot at an angle of depression of 34 degrees. What is the horizontal distance between the hot air balloon and the landing spot to the nearest foot? Very similar to the last one. We have a hot air balloon. If you're artsy, you can make these really pretty, I guess. That's not a very good hot air balloon. There we go. She is 30 feet above the ground. Notice we're still going to make triangles. She has a horizontal line of sight, and her angle of depression is 34 degrees. Obviously not quite drawn to scale. It asks, what is the horizontal distance from her to the landing pad? So x here. Okay, horizontal distance just means it's this one. It's not trying to find this distance here. So, once again, we have to find a degree inside of the triangle, so we can either find this one or this one. I'm going to do the alternate interior idea this time, knowing that the angle of elevation and the angle of depression are congruent to each other. So this is 34 degrees. This is my perspective point, so I have opposite, I have adjacent. That means I'm going to use tangent again. So we have tangent of 34 is equal to opposite over adjacent. And then we go ahead and solve. Notice if the x is in the denominator, you do have to do some cross multiplying. Running out of space. So So x is going to equal 30 over tangent of 30 to 34 degrees. So we want to go ahead and say, alrighty, 30 divided by tangent of 34. And the horizontal distance to the nearest foot is 44 feet. So this distance here is 44 feet. All right, if you had instead used this degree and did opposite and over adjacent, you would also get 44 feet for the solution there. All right, another problem. Vernon is on the top deck of a cruise ship and observes two dolphins following each other directly away from the ship in a straight line. Vernon's position is 54 meters above sea level, and the angles of depression to the two dolphins are 35 degrees and 36 degrees. Find the distance between the two dolphins to the nearest meter. So, we've got a lot to do here. We need to find the distance here, this whole distance, to the further away dolphin, and then we need to do the same thing for the distance to the nearer dolphin. And then you have to subtract those to find the real piece between J and K that we are looking for. So I'll just leave that colorful, I suppose. We're going to find, I'll recolor it as we go, I guess. We are going to find the furthest away dolphin's distance first. So this will be what I call X, from J to L in our picture. So that angle of depression is 34 degrees. I am going to subtract that from 90. And I'm going to take 90 minus 35 and get 55 degrees for this guy. Okay, so this is my perspective point, meaning I'm trying to find the opposite and I'm given the adjacent. So I'm using tangent. We're just doing tangent like crazy today. We have tangent of 55. Whoops, typo, 55. There we go. This is 55 degrees. Tangent of 55 is equal to opposite over adjacent. Go ahead and solve. We have 154 tangent of 55 is equal to 219. Whoops. We round up. Let's say 220 meters. Okay? Then we need to do a similar thing, except now we find the distance to the closer dolphin, which I originally had in purple. We need to find this degree, so that would be 54. And then we are trying to find this distance between K and L. I'm going to call that Y. So now we have tangent of 54 is equal to Y over also 154 meters. And then you solve basically the exact same, except the only thing that changes is the degrees. So we have 154 times tangent of 54 degrees, and we get that this dolphin is 212 meters away. So the distance between the dolphins is actually 220 minus 212 is 8 meters. So there's 8 meters between the dolphins. All right, that's about 24 feet, a little bigger than that. So that's just 2 problems in one, basically, where you then have to find the final answer, which was that guy right there. Crazy how much 1 degree elevation of depression makes a difference in the actual distance away. All right, last problem. Madison took out her 2nd floor window, which is 15 feet above the ground. She observes 2 parked cars. 1 car is parked along the curb directly in front of her window, and the other car is parked directly across the street from the first car. The angles of depression of Madison's line of sight to the cars are 17 and 31 degrees. Find the distance between the 2 cars to the nearest foot. So this is like basically the same as the dolphin one. We have the window. This is 15 feet up. There's 2 cars. We have this car. I'm just going to draw them in circles because I'm not an artist. And this car. Okay. The angles of depression of Madison's line of sight are 34 degrees to this car. Sorry, 31 degrees. And then to this car, it is 17 degrees. Okay, so we want to find this distance. And we want to find this distance. And then our final answer is actually the distance between them. Okay, so let's actually shrink this down. And then I'm going to once again find out the remaining complement here. So we take 90 minus 17. And we get 73 degrees. I'm going to use that. And then I take 90 minus 31. I get 58 degrees. And I will use that. So this one has been very tangent oriented today. We have our perspective here. We have our adjacent, and we are trying to find our opposite. Means we're using tangent again. So we have tangent of our degree, 59, is equal to opposite over adjacent. So hopefully we get really good at using this tangent at least. Cosine and sine look similar, except sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. We go ahead and solve 15 tangent of 59 degrees, and we get that this particular car, the close one, is 25, we'll round up, 25 feet from her building. And then if we find the distance of the further away car, we are going to use tangent once again. This time it's tangent of 73 degrees is equal to opposite, I'm going to call y, over adjacent, which is 15. Once again, multiply by 15 on both sides. We get 15 tangent of 73 degrees. And this car is 49 feet away. So if you subtract these two, you end up getting our final solution, or how much space is between them. And there are 24 feet between the cars. Alrighty. Have a great day, everybody.